In this video, we're going to take a look at how we can use the quantum model of the atom, as well as a concept called hybridization, in order to explain how bonds are formed in a covalent compounds. So we first need to sort of talk about, well, how are covalent bonds formed in the first place? We know from previous courses and what we've seen in chemistry that covalent bonds are formed from sharing of electrons. And so if we take this definition then of covalent bonds being formed by shared electrons, then and bringing in the quantum model of the atom, then a covalent bond is formed when two half-filled orbitals overlap. And so what happens when we get orbitals overlapping is we get a new combined orbital that contains two electrons that have the opposite spins. So for example, if we took hydrogen, hydrogen has just one electron in its 1s orbital. So if we take two hydrogens, we know that they form a covalent bond, each having one electron in a 1s. So when the two 1s's overlap, this is what its covalent bond looks like, and so it would then have a fully filled 1s orbital. One electron coming from one hydrogen and one electron coming from the other hydrogen. So another example could be something like HF. This will form a covalent bond as well, where there's one electron in a 1s orbital from the hydrogen, and then fluorine, if we looked at the 2p, it has two of them are completely filled and one is half filled. So the half filled one is able to then overlap with the 1s. You get this overlap happening here, forming a covalent bond and fully filled orbitals. Okay, that's all great and dandy, but what if we look at carbon? So let's kind of first take a look. If we have the energy level diagram or the orbital diagram for carbon, so we got energy there, we got 1s, 2s, and then the 2p's. And carbon has 6 electrons, so we'll put 2 here, we'll put 2 here, so that's 4, 5, and 6. Okay, so based on kind of what we've talked about already in this video, we have two 2p orbitals with one electron in each. So you would think that carbon would only form 2 bonds, but carbon will actually form 4 bonds of equal energy and equal length. So how the heck is this possible? Well, essentially what we can do is we can use something called hybrid orbitals, or we can take the 2 electrons in the 2s, so this 2s orbital, combine it with the 3 2p orbitals to create 4 new orbitals of equal energy and equal strength to create those 4 orbitals that have 1 electron in each so that we can form 4 bonds. So this is what really hybrid orbitals are about. In carbon, for example, the 2 2s electrons and the 2 2p electrons are going to form 4 new orbitals that are hybrid, and they're called sp3. We'll go into why in a moment, that have 1 bonding electron in each. So these sp3 hybrid orbitals are what form the tetrahedral shape. Now, really important to note, hybrid orbitals only exist when bonding occurs. So they don't exist in an isolated atom. They only exist when we start getting bonding. So for carbon, instead of this 1s here, and then 2s and 3 2p orbitals, let's just erase this because, actually, no, you know what? We're going to show it. But instead of these 4 orbitals are going to combine to create 4 new hybrid orbitals. So they're actually going to be a little bit higher than 2s, but a little bit lower than 2p. And so these would all be sp3 hybrid orbitals. sp3, and that one's 2sp3, and each one then would have one electron in it. So that's how we can form our 4 bonds. Okay, so can we use similar reasoning with BF3? Well, if we take a look at boron and we look at its energy level diagram, we got a fully filled 1s, then we got 2s with 2 electrons, and then the 2 p's, we have 1. But boron forms 3 bonds of equal strength and length. So in order to do that, we're going to take some of our orbitals and we're actually going to create 3 hybrid orbitals, and we're going to have a 2p orbital left over. So these hybrid orbitals here are called sp2. And that's because we're going to take 1s and we're going to take 2 of the 2p's to create 3 new orbitals that are equal energy and equal strength, and we're going to have a 2p orbital left over. Okay, so this is where our 3 bonds are coming from. So these we would say are sp2 hybrid orbitals. So how do you know what kind of hybrid orbitals are formed? Well, really, they're based on the electron domain geometry. So they're not necessarily based on the shape itself, but on the electron domain geometry. So for linear shapes, the atomic orbitals that get mixed is 1s and one of the 3 p orbitals. So it's going to form 2 sp hybrid orbitals. So it's taking 1s and 1p and hybridizing the 2 of those. There are going to be 2 p orbitals left over that are unhybridized, and the only possible molecular geometry related to that are linear. So if you have a linear molecule, you know you have sp hybrid orbitals. For the trigonal planar shape, this is going to have 1s and 2 of the 3 p orbitals mixed together to create 3 sp2 hybrid orbitals. There's going to be 1 p left over, and this can happen for VSEPR shapes that are either trigonal planar or V-shaped, or the other name for that is bent. For tetrahedral, we're taking an S and we're taking all 3 of the P's. So we're going to make 4. You can see how the numbers add up here, right? 1 and 3 make 4. And then the sp3 is because we have 1s and we have 3 p's. There will be no unhybridized orbitals left over. And so anytime you see a VSEPR shape that's tetrahedral, trigonal pyramidal, or bent with the 2 lone pairs of electrons, they have sp3 hybrid orbitals. Now it's kind of important to point out here, like if you have trigonal pyramidal or bent, yes, they still have sp3 hybrid orbitals. The lone pair of electrons actually sits in one of these, or sits in the place of one of these hybrid orbitals. So while it's not really technically a hybrid orbital, it still is taking the place of that hybrid orbital. So kind of worthwhile to know that you are basing hybrid orbitals on electron domain geometry and not necessarily on what the molecular geometry is. Okay, if we continue on, you can sort of see a trend here for trigonal bipyramidal shapes. So these are our 5 electron domain geometries. We need 5 orbitals to hybridize. So we're going to take 1s, 3 p's, and then the next one up is d. So we'll take one of the d's. That is going to make 5 sp3d hybrid orbitals. There are 4 there are 4 d orbitals that are unhybridized. And so anytime you see a trigonal bipyramidal, seesaw, T-shaped, or linear shape, they will have sp3d hybrid orbitals. Finally, octahedral, or the 6 electron domain geometries, they'll have 1s, 3 p's, and 2 of the d's hybridized to make 6 sp3d2 hybrid orbitals. There are 3 d orbitals that are unhybridized, and so this is for octahedral, square pyramidal, or square planar shape. So really, you need to know the summary chart. You need to know where hybrid orbitals come from and how hybrid orbitals create covalent bonds. That's it then for this video. We'll see you in the next one.